Shall I start? Okay, guys. Good evening to everyone out there who is eagerly waiting for us to start the session. So, welcome to AlgoRun, an event which will give you an insight about the crucial and essential part of your placements. That is DSA, which is also known as data structures and algorithms, and time complexity. So, this session will take you into the depth of data structures, its types, and various common examples like linked lists, arrays, tags, and queues, etc. And most importantly, the time complexity. So we would like to begin the session by thanking all the people present here and the core committee members of the IEEE Industry Application Society. My name is Shashank Kota, and I'm currently working as a core member in the chapter, particularly in the technical domain. IEEE-IAS is a chapter which is a backbone for some of the biggest technical events and conferences held in the past. The chapter is esteemed to conduct regular meets, technical events, and hackathons to motivate and bring out the creativity and curiosity out of the student. For today's event, I'm speaking along with my partner Naima Khatun, who is also a core member in the technical domain. With this, I end the welcome note, and I hope you all enjoy this informative session. So let's, yeah, can you move the slide? So first, let's get into the introduction to DSA, that is data and information. First of all, let's start with the definition of data. What is data? Most of you will be knowing the meaning of data. That is, it's basically a collection of different numbers, symbols, and alphabets, which particularly represents information. So information is defined as a collection of data. A data structure is a group of elements that provides the easiest way for the computer to perform actions. Computer cannot produce information without the help of sequence of steps, that is basically algorithm. So algorithm is basically the sequence of steps which is used to solve a problem. The processed information is later stored in the computer's memory. The main aim of DSA is to reduce the time complexity and the memory for better efficiency and storage. Next slide. Yeah, so now let's get into the types of data structures. There are basically and mainly two types of data structures, that is linear and nonlinear. Here are some of the examples. So in the slide, you can see singly linked list, memory location index, that is for arrays, stacks, and queues, etc. And this is a binary tree. So now let's get into the types of data structures. So there are two types I mentioned in the earlier slide, linear and nonlinear. So linear data structures are the type of data structures where the elements in it are arranged in an organized and sequenced manner. So some of the examples are list, queue, and stack. A real life example can be bank and movie counters where people stand in queues to collect tickets. Non-linear data structures are the type of structures where the elements are not arranged in an organized and sequenced manner. So it basically appears to be scattered everywhere. The elements in this are are arranged in more than one dimension. So it can be two, it can be three, can be how much ever you want. Example, trees and graphs. So trees, we have seen the branches, so they are literally scattered everywhere, right? So this is an example of a non-linear data type structure. So now we have seen the types of data structure. Now the last thing is the application of data structures. Always remember that data structures and algorithms are the core for placements. They are very much required for you to grab a good package. So this is on a personal application. So apart from the personal, the other advantages and applications of data structures are operating systems, image processing, simulation, and blockchain technology. So by blockchain technology, you must have heard about NFTs and cryptocurrency. Now we have seen data and data structures. Now what's left is algorithms. So we have seen about the data structures in the previous slides. Now what's left is algorithms. Big companies like Amazon, Microsoft, Meta, etc. come to hire graduates and professionals who are expecting DSA. Therefore, it is very important to learn this topic. Algorithm is basically that's what I mentioned in the earlier slide. Algorithm is a sequence of steps or instructions used to solve a problem. Simple example is addition of numbers. So what do you need to add two numbers? The solution to these problems are mentioned in steps. So first we'll start with step one. Step one is to start the problem. Step two is to take two numbers A and B. Step three is to take another number C. Step four is to assign C and add both the numbers. It is used to assign and add both the numbers. So step 5 is to print the result, which is C, which is further equal to A plus B. Step 6 is to stop the process. So I hope
Computer
you
science.
all understood the basic introduction and importance of DSA. Now I'm moving on to the time complexity part, which will be explained by my partner Naima Khatun. On to.
Yes. Yes. So our next topic is time complexity. In computer science, analysis of algorithms is crucial. It is important to find the most efficient algorithm to solve a problem. It is possible to have many different algorithms to solve a problem, but the challenge here is to choose the most efficient one. Now, the point is, how can we recognize the most efficient algorithm when we have a set of different algorithms for solving a problem? We do this by studying time and space complexity. In this session, we will be discussing time complexity in detail. What is time complexity? Time complexity is a programming term that quantifies the amount of time it takes a sequence of code or an algorithm to process or execute in proportion to the size and cost of input. So time complexity shows how time taken to execute an algorithm grows with the size of input. So the time complexity is the number of operations it takes to perform a task, to complete the task. It is important to understand that the algorithm that can complete the task in the least number of operations is considered the most efficient one in terms of time complexity. However, time and, time and space complexity are also affected by factors such as your operating system and hardware, but we are not including them in this discussion. Let's take an example. Take a look at this piece of code. There are three separate statements in this code inside the main function. The overall time complexity is constant time, big O of 1, because each statement takes only unit time to print the statements. Now take a look at this example. Here we have the same chunk of code, the same three statements inside a for loop, and it repeats for n number of iterations. So here the time complexity becomes n multiplied by big O of 1, which is big O of n. You could say that when an algorithm employs statements that are executed only once, the time required grows as the number of times the loop is set to run grows. When an algorithm has a mix of single executed statements and loop statements, the time required increases according to the number of time each statement is run. For example, if you have a recursive function and the recursive function is called multiple times, identifying and recognizing the source of its time complexity may help reduce the overall processing time, and that's exactly what time complexity analysis aims to achieve. Now, what exactly is big O? I've been telling you big O of 1 and big O of n. So, what exactly is big O? In DSA, in data structures and algorithms, big O is simply called order of. But mathematically, big O of n can is equal to big O of n square. It can also be big O of n cube, and it can also be big O of n power 4, and so on. I will prove this to you in a while. Here's a graphical representation of big O. The x-axis represents the size of array. The size of input. And the y-axis represents the runtime, the time taken by the algorithm to complete the task. Here, the straight line parallel to the x-axis represents constant time, meaning no matter how big the size of input is, no matter what the size of input is or how many elements, the time taken to complete the task remains constant, meaning it does not depend on the size of input, and that's constant time. This dotted line represents linear time, meaning it is proportional to the size of input. As the size of input grows, so does the time taken to complete the task. Asymptotic notations. What's asymptotic notation? Asymptotic notations give us an idea of how good an algorithm is compared to another algorithm. Primarily, there are three types of asymptotic notations used: big O, big omega, and big theta. First, we have the big O notation. Big O notation is used to describe asymptotic upper bound. Mathematically, a function fn is said to be big O of gn if and only if there exists positive constants c and n naught such that 0 is less than or equal to fn less than or equal to cgn for all n greater than or equal to n naught. So what does this mean? Let's write down the equation. Or let me tell you that here c is a constant. C is a constant and Gn is whatever you write inside big O. And N is the size of input. So let me write these down. Gn is whatever you write inside big O and N is the size of input. And C is a constant for all n greater than or equal to n naught. So let me explain you. Let's write down the equation according to the definition of big O first. Big O is 0 is less than equal to fn less than equal to cgn for all n greater than equal to n naught. Here we have to find a constant c such that the equation is satisfied for all n greater than equal to n naught. Also, we need to find a number n naught such that any number that is greater than or equal to n naught will satisfy the equation. So now, ultimately, if you succeed in finding the constants c and n naught, then according to the definition, such that the equation is satisfied, then according to the definition, fn will be big O of gn. Let me show you with the help of an example. Let's say fn is a function n cube plus 1. And let we have to see if gn is n power 4. So now let me substitute the values. According to the definition, we know the equation is 0 less than or equal to fn less than or equal to cgn for all n greater than equal to n naught. Now let me substitute the values of fn. Substitute values of fn and gn. Now we're going to find a constant c such that the equation is satisfied. Let's take the value of n naught as 2. So n will be 2 because we know the condition n will be anything that is greater than or equal to n naught. So on substituting the values of n in this equation, we get this is 9 and 2 power 4 is 16. Now we can see that 16 is greater than 9. So the equation is satisfied when the value of c is 1. Therefore, so we find that the equation of big O is satisfied for the value c is equal to 1. Therefore, according to the definition, fn is big O of gn when the equation is satisfied. So n cube plus 1 is big O of n power 4. Now, if you remember, earlier I told you that big O of n is also big O of n squared, which is also big O of n cube, which is also big O of n power 4, and so on. Let's verify that now. Let's have a function fn as n cube plus 1, the same function, and let's take gn as n cube this time. So my equation is going to look like 0 is less than or equal to n cube plus 1, less than or equal to c n cube for all n greater than or equal to n naught. Again, we have to find a constant c such that the equation is satisfied. Let's take n naught as 2. Again, n will be 2 because we know the condition n is anything that's greater than or equal to n naught. So let's start with 2. So here's the equation, and on substituting the values of n in the equation, we get 9 and n cube is 8 when c is 1. So 8 is smaller than 9. So we see that this does not work. The equation is not satisfied for c is equal to 1. So let's take a different value of c. Let's take c as 2. Now 0 is less than equal to n cube plus 1, less than equal to c n cube. This would be 9. 9 again, and n cube is 8 and c is 2. Let me write it in a better way. So taking the value of c2, this will be 9 and n cube is 8 and c is 2. So 2 multiplied by 8 gives you 16, and 16 is now greater than 9. So c n cube is greater than n cube plus 1, and the equation is satisfied now for the value of c2. So now from the last two examples, we see that fn is big O of n cube as well as big O of n power 4, but for different values of c. Therefore, we may conclude that fn is big O of gn. So n cube plus 1 is big O of n cube. Also, n cube plus 1 is big O of n power 4, which is in accordance with the definition of big O. Here's a graphical representation of big O. Here we see in this graph, the graph of CGN is always above Fn. CGN is always greater than Fn after a certain value n naught. And this is exactly what the definition of big O says. Moving on to the next asymptotic notation, big omega. Big omega is used to describe asymptotic lower bound. A function fn is said to be big O of gn if and only if there exists positive constants c and n naught such that 0 is less than or equal to cgn, which is less than or equal to fn for all n greater than or equal to n naught. Now we see that the definition of big omega is very similar to that of big O. All you have to do is swap the values, swap CGN and FN from the definition of big O, and do this in the graph as well. And there you have the equation, the definition and graph of big omega. Let me explain you with the help of an example. Here's the equation of big omega: 0 less than or equal to CGN less than equal to Fn. and the condition always remains same for n greater than or equal to n naught. Let me help you understand with the help of an example. Let fn be the same function n cube plus 1 again, and I can tell you that n cube plus 1 is big omega of 1. Let me show you how. Let's also take g of n as 1. And so the equation would now be 0 less than equal to c of c gn. Gn is 1, so I write 1 here. And fn is n cube plus 1 for all n greater than or equal to n naught. So now we have to find a constant c such that this equation is satisfied. Let's try for n naught equal to 1. So n will be 1. So this will be 2. And if we take c as 1, this will be 1. So 2 is obviously greater than 1. So the equation is satisfied when c is equal to 1. Therefore, I say that n cube plus 1 is big omega of 1. So I hope you have understood this. Moving on. Here's a graphical representation of big omega. Here, Fn is always above Cgn, just like what we saw in the definition, after a certain value n naught. For any n that is greater than or equal to n naught. You know that n represents the size of input, and the y-axis has time, the runtime of the algorithm. So for any n that is greater than or equal to n naught, Fn is always above Cgn, and that's exactly what the definition of big omega says. Moving on to the next asymptotic notation, big theta. A function fn is said to be big theta of gn if and only if fn is both big O of gn and big omega of gn. So what's the equation? What was the equation of big O? It was 0 less than equal to fn less than or equal to c1 cgn. Let's take the constant as c1 to avoid confusion. The condition is always the same for n greater than or equal to n naught. And this is the equation of omega, big omega, 0 less than or equal to c2gn less than or equal to fn for all n greater than or equal to n naught. So big theta of gn is both big O of gn and big omega of gn. Merging these two equations, we get 0 less than or equal to c2gn less than or equal to fn less than or equal to c1gn for all n greater than or equal to n naught. So we can say that a function fn is said to be big theta of gn if and only if there exists positive constants c1, c2, and n naught such that 0 is less than or equal to c2gn, less than or equal to fn, less than equal to c1gn for all n greater than or equal to n naught. Here's a graphical representation of big theta. We see that Fn is sandwiched between C1gn and C2gn. This provides both the upper bound and the lower bound, which is why big theta gives a good picture of time complexity of an algorithm. Big theta gives a better picture than big O and big omega, and that's why this is preferred. Using big theta is preferred. Here we have the common runtimes in the increasing order. Big O of 1, big O of log n, big O of n, and so on until big O of n power n, with big O of 1 being the best and big O of n power n being the worst kind of runtime of an algorithm. Let me help you understand this better with the help of a graphical representations. We see first we have big O of 1, which is constant time, which is called constant time, meaning the runtime does not depend on the size of the input. No matter how big the input is, no matter how many elements you have, the time taken to complete the task remains constant. It does not depend on the size of input. Next, we have big O of log n, which is better than linear time. The increase in runtime as compared to the increase in size of input, the number of elements is very little. So that's good. Next, we have big O of n, which is called linear time. So here the time taken is proportional to the number of operation, to the size of input. And the rest, big O of n log n, big O of n square, big O of 2 power n, and big O of n factorial are expensive in terms of time complexity, meaning they aren't much efficient. Best case, worst case, and average case in time complexity. Let me help you understand this concept with the help of an example. Let us consider a sorted array with 10 elements, or you may consider a sorted array with n number of elements where n is the last element. And we're given a task. The task is to find a number. Let's say the number is called search digit. Let's say the number is search digit. Our task is to find if the search digit is present in this array. So there are two ways. Let's say there are two ways to do this task. So two algorithms, Algo 1 and Algo 2. Algo 1 says start from the first element until an element greater than or equal to the search digit is found. Meaning the search digit is going to be compared to each and every element of this array until the search digit matches any one of these. Algorithm 2. Algo 2 says check if the first or the last element is equal to the search digit. If not, find the middle element in the array and if the middle element is greater than the search digit, eliminate the second half and proceed with the first half. Repeat the process for the first half. Let's say the search digit is 4. Let's say the search digit is 4. And so according to the first step, the algorithm is going to first check if the search digit is equal to the first and the last element. In our case, it's not because the search digit is 4. Now, the next step is to find the middle element. Let's say the middle element is 6 approximately, and we have to check. It's going to check if the search digit is greater than, if the middle element is greater than or lesser than the search digit. In our case, the middle element is greater than the search digit. So we're going to eliminate the second half of the array, and the process is we're going to repeat the process only for the first half. So at every step, half of the input is going to be eliminated. And that's how this algorithm works. Now let's analyze the algorithms. Let's analyze Algo 1. Here, the best case scenario would be when the search digit is 1, because that's the very first element. In this case, when the search digit is 1, no matter how big the array is, no matter how many elements the array consists of, the time remains constant because the search digit is found in the very first step. Hence, the time complexity is big O of 1. It's constant time. The worst case would be when the search digit is the last element of the array. If it's an array of length 10, where 10 is the last element, so that's 10 being the search digit would be the worst case. And if it's an array of size n, then n being the last element, then n being the search digit would be the worst case. Because in that case, each and every element, the search digit is going to be compared to each and every element. So there's going to be n number of comparisons. So the time complexity would be linear time, big O of n. Average case is sum of all possible runtimes divided by total number of possibilities. Calculating average case can sometimes become very complicated. Analyzing algo 2. Let's analyze algo 2. What would be the best case? The best case would again be when the search digit is 1, that is the very first element of the array. Because again, no matter what the size of the array is, what the size of the input is, the time taken is going to remain constant because there's only one comparison to be made and the answer is found. The worst case would be having a random element because in this case the array would have it's gonna divide the array into half at every step until a single element is found. To help you better understand, let's look at a few examples to help you better understand time complexity. In this code, we have hello world. Hello world is printed only once. So regardless of the operating system or the computer configuration that you're using, the time complexity is constant time. In the next example, take a look at this piece of code. When a function checks all the values in an input data set, or when it needs to iterate through every value in the input, it is said to have time complexity of order n. Example, say that is printed 5 times, which is the value of n. It is directly dependent on the size of the input variable. So we say that the time complexity is of the order of n. Next, we have big O of n squared. Now, when the running time of an algo increases non-linearly with the length of the input, it is said to have non-linear time complexity. One loop takes big O of n, and if the function includes loops inside loops, it takes n multiplied by n, which becomes big O of n squared. In this example, there are 2 nested loops. So the inner loop would the inner loop would print the statement m number of times, and the outer loop, and it would again be printed according to the input of n, which is the outer loop. So ultimately, it's going to be big O of n multiplied by m. 3 into 2 in this case. So it's going to be printed 6 times. So if n was equal to m, it would be big O of m squared. And next, the last one, we have big O of log n. This is the same thing that I had explained earlier, which was algo 2, which was binary search. And algo 2, big O of log n, is obviously better than big O of n, which is linear time, because half of the input is going to be eliminated at each step until a single element is found. So it doesn't have to compare with each and every element of the array. The operation does not take place on each and every element of the input, and so the time taken will obviously be less. It gets halved each time. And this is the end of my presentation, and I hope you all have understood what time complexity is. Thank you. Okay. So in this session, we have learned about DSA and its applications. We have also learned about the importance of DSA, and we have also learned about time complexity. In the future sessions, we will talk more about the topics of data structures and algorithms. We will talk about arrays, lists, and trees. Any questions? Also, thank you everyone for joining in, and have a good night.